All right, we are back for chapter 5, continuation, and we had stopped at the point where we're about to start building a full application for Caesar Cipher, both encoding, decoding, and also cracking the code. Okay. Uh, just before this, before we get to this, let's look at 2 or 3 functions which we developed beforehand, which will be useful here. Okay. And actually what I did was I went ahead and took all the code for the Caesar cipher problem and put it into this notebook here, okay, or this, yeah, that's right, this notebook or notepad. And you can see uh, it starts with the import, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There are 13 different functions which are defined here, okay, to actually solve the whole Caesar ciphers problem, okay. But of these 13, the first 3 we have already discussed while we discussed list comprehensions, okay. And you can actually see that list comprehensions are used throughout this problem, okay. Let's count, if you want, let's count how many list comprehensions are used. There's 1 here, 1, 2, 3, 4, 5, 6, 7. Okay, so there are 7 places we can see list comprehensions have been used. Okay, so this is actually an excellent problem to solve, or at least look at the code to see how list comprehensions play a role in problem solving in Haskell. Okay, so hopefully by the time we complete this this particular program, okay, all of you would be comfortable using list comprehensions, not just how they work, but where to use them, and so on. Okay, so that the second part on when to use them and where to use them is basically part of your problem solving skills, right? Anyway, so that's what it is, and we have discussed these 3 functions before, okay. And I think the remaining 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the remaining 10 we're going to discuss and see how these 13 functions put together produces a solution to the Caesar cipher problem, okay. Let's recap these 3 functions, okay. The positions function takes an item from a list and a list of items and returns the indices where this item appears, okay. So it's like the index of, but multiple indices, okay. So this is going to be useful. And the second is count how many times a particular item or character in this case, okay, appears in a string. How many times does a particular letter appear in a string, okay. And the third is how many times lowercase letters appear in a string, okay. So those are the 3: positions, count, and lowers, okay. Just keep those 3 in the mind, and soon we will start seeing those 3 being used, okay. Okay, now let's define the problem. What is this problem? What are we trying to write a program for? Okay, the problem is that there is a cipher coding method or cipher method called Caesar cipher. It's actually very naive and simplistic. Okay, and what you do is you take plain text in English. Let's say we'll take it English. I guess the same idea can be translated to other languages, but let's take English sentences or messages, if you want to call them, okay, plain text messages, and we use a shift factor, okay, shift factor to develop a code, okay, or the cipher. It's called the Caesar cipher. And that shift factor, what it does is that it shifts each letter in the alphabet A through Z by those many positions, and generates a new letter or a coded version of that letter, okay. And because this shift factor can take you around the alphabet, so for example A can become a K or something like that, you see, and so on, we need to worry about what happens when we add the shift factor towards the end of the alphabet Z, and for that we will use a circular definition, and that after Z the next letter would be A, okay. After A will be B, after B will be C, after C will be D, and so on. After P will be Q, and after U will be V, and Y, after Y will be Z. And after Z, we will consider the next letter to be A. Okay, so you can think of all the letters A through Z organized in a circular manner. Okay. All right, so the shift, you probably have seen this before, okay? So here's an example. Suppose you take the string Haskell is fun, okay? That's a string. And you use a shift factor of 3, okay? What does it mean? It means that A becomes D, okay? You shift by 3 positions the letter A and you get D, right? One position will be B, the second position will be C, and then the third position would be D. See, when you shift or when you move in this circular manner, you'd get D for A, okay? And so on. H will become a K, S will become a V, and so on. And what will happen is that this particular, with a shift factor of 3, with a shift factor of 3, Haskell is fun will become this string, okay? KDVNHOO space, okay, all the spaces and other things will have to be respected, and then the LV space IXQ. Okay, so that's the idea here. Okay, a shift factor allows you to take a plain text message like Haskell is fun and code it. Okay. And what we're going to do here in this project, if you want to call this a project, okay, Caesar Cipher project, okay, is we're going to develop three functions, okay. One to encode that is given a string and given a shift factor how to generate the coded version of the string, okay. So this is called the plain text. This Haskell is fun is called a plain text, and this KDV and this thing is called the cipher text, okay, or the coded text, okay. So this is called encoding. Now the decoding is actually trivial because if you encode with a negative shift factor, it becomes decoding, okay. So there is no separate method for decoding, okay, because this is a very simplistic method, Caesar cipher, and there's only one function for encoding and decoding, okay. If you use a positive shift factor, now technically you could use a negative shift factor to encode as well, so you can go backwards if you want, okay. But because it's circular, technically a negative shift factor can be translated into a positive shift factor, and you get the same thing. Okay. Anyway, there's no separate method to decode. That's the point I was trying to make. Okay, because you can just use the negative of the shift, and so if the shift was already negative, then you use the positive of the shift to decode. Okay. All right. So the first two things we are going to do is make sure we can do encoding and decoding, and then we are going to look at how to crack, that is, how to guess the shift factor when a cipher text is given or a coded text is given to us. Okay, how to guess, okay, and crack it, and then go backwards from this to that without knowing the shift factor. Of course, if you're given the shift factor, then you're given the key. This thing is called the key of a cipher. Okay, the shift factor here. Okay. So we're going to write a program or write many functions, which is going to allow us to crack. Now it may not be perfect, and it may crack in 80% of the time, but sometimes you may not get the correct answer. Okay, but anyway, we are going to attempt to do that. Okay, so that's the project about. Okay, but let's take care of the simpler stuff first, and that is the encoding and decoding. That's the simpler stuff. Okay, all right. Okay. So we would use this data.char library a lot here because there are some useful functions there. I think in the previous homework also, you guys are using some ORD and conversion between characters and letters and integers and so on. Okay, there's a function called ORD, O-R-D, which gives you the ordinal value of characters. Okay. And it's actually an integer, a unique integer, which corresponds to the ASCII code typically. So anyway, it allows you to convert a character into a number. That's what it does, the ORD. Okay, so we're going to use that, and that is a backward conversion called CHR, which takes the odd value and makes a character out of that. Okay, so these are the two functions we're going to use: ORD and character. CHR. Okay, So one other thing in this whole project, yeah, that's right, we'll encode only lowercase letters, and if there is an uppercase letter in the code, we'll leave it alone. We won't bother with that. Okay, this is just a simplification. If you want, I mean, it's so that, I mean, the point here is not to really write a super. First of all, it's not a interesting cipher. Okay, anybody can break it, so crack it, see. So that's, and secondly, it's just an example. So we are limiting ourselves to lowercase letter. I mean, the input can have uppercase letters, but those will not be coded. They'll just remain as it is. Okay. Or another way to think of this is that we'll assume that there's no uppercase letters in the input. Okay. So but if there is, then we'll leave them alone. Okay. And of course, if there are numbers and digits and commas and semicolons, we leave them alone as well. Okay, so we just simplification here. Okay, for simplicity, we'll encode only lowercase letters and leave every other letter the same. Okay, okay. Now our first step here is to build two functions which allow us to move back and forth between characters and the not the, yeah, I guess the ordinal value. Okay, yeah, ordinal value. Okay. Technically, yeah, not the ordinal value, but we're going to assume 0, basically a conversion from A to 0, B to 1, and Z to 25. Okay, so each of the letters has a position in the alphabet, right? And assuming starting at 0. So we want two functions which allows us to go back and forth between the A through Z and 0 to 25. Okay, got it? A maps to 0, or 0 maps to A, back and forth. Okay, so we want two such functions, and here are those two functions, and we call it letter to integer and integer to letter. Okay, let to int and int to let. Okay, let to int takes a character as input and produces integer as output, and that integer would be the index in that 0 to 25 of that letter. Okay, and the way to get that is very straightforward. Let to int of C equals, you get the ordinal value of C, the character, okay, for which you want to convert. And since the ordinal values are sequential, that is, the ordinal value of B is 1 more than the ordinal value of A. I think it is 97 is the ordinal value of A, or 96, something like that. And then they go in sequence. So when you subtract the ordinal value of a character or ordinal value of A from the ordinal value of a character, you'll actually get this position, okay, 0 to 25. Okay. And that's what we do, odd C minus odd A. Okay, so this should give you the integer version of the letter. Okay, and the other one, int to let, given an integer, it returns a character, and the integer which is given we'll assume it is between 0 and 25. Okay, we can safely assume that. Okay, so how does it do that? It takes the integer n, which is given to us, and we add odd A to it. Okay, because that's how we subtracted here on the top there, right? So we add odd A into it, and then you'll get a new ordinal value for this n position, and that when you apply the CHR function, it gives you the character. Okay, here's a simple illustration of back and forth. Okay, so I'm going to run this cell. Oh, that was the higher cell. Run this, run this, run this, and run that. Okay, so you can see that let to int of A gave me a 0, let to int of n gave me a 13. Okay, n happens to be the first letter in the second half of the alphabet. Okay, and 13 is the beginning of the second half of the alphabet. Okay, A is the first letter, so that's where we get the 0 there, and n is 13. Okay, and if you go backwards, int to let of 0 should give us A, and int to let of 13 should give us n. Okay, so make sure that you don't call this on a number other than 0 to 25. Okay, between that. Okay, and also don't provide a character, although you may get a value, but we're not going to use it for anything else. Okay, so that's. No questions about this. So these are the two functions we developed. Okay, besides the 3 which we already have here. Okay, remember the positions, count, and lowers. These 3 we have already developed, and here are the other 2. We just okay. So we have covered 5 of the 13 functions we are at. Okay, now let's develop a shifting function. Okay, because this whole Caesar cipher requires us to take a letter and shift it by the shift factor, right? So that's the function we're going to write, a shift. Okay, what does shift do? It takes the shift value, okay, and it takes a character like a A or a B or a C, something like that, or it could be something other than lowercase too, right? And then it returns the coded version of that. Okay, the shift will code a letter. Okay, a single letter. So it will not code the whole thing, the whole string, but it will just code a single letter. Okay, so this is a function which encodes a single character. Okay, using the shift factor. So it takes two inputs, N and C, and I'm using the guards notation. So if the C is a lowercase letter, right? So this is lower is a function in data.char. If it's a lowercase letter, then I can code it, right? Then what I do is I take the C, convert it into an integer, okay, and then add the shift, okay. So take the character, convert it into integer so that you get the integer version of that, and add the shift. Now when you add the shift could be a large number like 20 or 18 or something like that, and then this will take you beyond the 25. Remember we said that it's a circular, so we had to do a mod 26 so that you can go around the Z and come back to ABC, okay. So you do mod 26 of the sum of N to the integer version of C, okay, and then convert the whole thing back to a letter, okay. So you start with the C, okay, convert it into an integer, add the shift with a mod of 26. So when you add, you go around, okay, and then convert it back to a letter, okay. So that's what is happening here in this expression, okay. It's a pretty straightforward expression, but that's what will code this. Okay. Now, if it is not a lowercase, which is otherwise, then we return the character as it is. Okay. So if it's uppercase or if it's a digit 1 or 2, we'll just return it as it is. Okay. All right. So here's some usage of shift. Okay. So that's the shift function, and here's a shift which has been copied here. So you can see that as we download the functions, we copy it into this big program, and we would get the entire project completed. Okay. So shift of 3 of H should give us a K. Remember, that was the example we looked at here. Haskell is fun. H shifted by 3 gives you a K, right? So that's what we got. Shift of 3 of a capital H or uppercase H should not change it. You see, that's why you got a capital H, because we do this coding only for lowercase letters, okay? And shift by 3 of a Y, now this will go around the Z, right? Y, when you add 3 to it, Y will go to Z, then to A, and then to B. So shifting of 3 of by 3 of Y should give us a B, and that's what you see here, okay? And if you take the B and shift it with -3, you get back the Y, okay? And that's what I said, that when you use the opposite shift factor, negative shift factor, you actually get back the decoding, okay? So that illustrates that, okay? And now we are almost done with the encoding, because using shift function, which shifts individual characters, and the list comprehension, we can actually do the encode. Here's an encode. Encode takes two inputs, the shift factor int and any string, and produces the coded version of the string, okay? And the way it does is that encode n of xs is x comes from xs, so that's the individual character in xs, okay? This is actually a string comprehension, which is nothing but a list comprehension. So x is each letter in that, and then what we output is we collect all the coded versions of each letter, okay? So if it's a lowercase, we'll get a coded version of that. If it's a uppercase, we'll get the same letter, and if it's anything else other than a lowercase, we'll get back the same thing, okay? And then this whole thing will be put together, because it's a list of characters, right? It'll become a string, okay? So that's all that is. So we finished the encoding and decoding, okay? So encode is the last function. So with these ones, encode, shift into let, and let to int, and lowers, count, and positions, with these 7 functions, 1, 2, 3, 4, 5, 6, 7, we have finished the first part of the project, which takes a string and encodes it. And if you provide the negative shift to the encode, you get the decode. So we are actually done with the encoding and decoding here, okay? So note that we do not need a separate function to decode, because providing a negative shift factor will automatically decode, okay? And here are a couple of examples of that, okay? Encode 3 of Haskell is fun will give us that KDB and HOO space LB space I, okay? And encode of -3 of this previous one, okay, would give us the original thing back. Okay, so take that and then minus 3, you get the original back. Okay, that's good. Okay, so it does work, the encoding, and well, this is the decoding technically. Okay, if you want, you can write a function. If you do want, you might write it as follows. Okay, let me show you how you would write a decode. Okay, using the negative shift factor. Okay, let me put it in this cell. Okay, you don't need, but suppose you say decode. Decode also takes an int and a string and returns a string, except that this string is the coded version, and then this is the decoded. Okay, so this definition would be pretty straightforward. You'll just call encode with a minus n. Now minus is always written this way, minus n, like that. Okay, of access. Okay, so that's how you might write a decode. Oh, okay. It says that why don't you use encode minus 1 itself? Why are you giving it a new name, kind of thing? And this is called the eta reduction from lambda calculus. We did not study eta reduction in lambda calculus, but it's one of those other beta reduction kind of things. Anyway, you can see that lambda calculus is embedded inside. But anyway, we won't do this. I'm going to delete it. Okay, I'm going to delete this cell, so we don't even have the decode. Okay, all you do is minus. Okay. All right, so we are done with that. So now let's come to the second part of this project, okay? And that is that we want to crack the code, okay? We want to guess the shift factor, okay? So given this coded string, okay? So somebody is giving this, or we might have intercepted this in the radio communication, okay? That in the World War II this was happening, okay? And that's why Turing became very famous, even though he was famous for Turing machines, but he worked a lot in the World War II as Cipher, cracking the code, okay? And there's a beautiful movie about him on cracking the code, kind of thing. See? So it's a good thing for computer scientists to learn that, okay? But anyway, the frequency table, the cracking the code, the Cipher code, Cipher Cipher code, Cipher ciphers is an interesting and not too difficult task, and that's what we're going to do now. Okay. All right. So we are given. So the problem now is we want to write a function. Given a code like this, a coded string like this, we want to find the. We want to decode it. Okay, without knowing the shift factor, without knowing that. Okay, we want to find out this. Okay, you might wonder how to do this. Okay, but the idea is that you can do this with frequency counts, and it's a simplistic observation from languages. All right, so we are going to look at how frequent certain letters appear in a natural language like English, and use that information to crack the code. Okay, so let's look at that. Frequency tables. So the ideas are explained, and some certain functions will be written, and then we'll finally write the crack function. Okay, the cracking the code function. The key to cracking Caesar cipher is the observation that some letters are more used, or I guess let's fix this, are used more frequently. There are a couple of mores here. Are used more frequently than others in English text. Okay, all of you know that the letter E is used the most. Okay, and there are some letters like Q and Z which are used very less. Okay. So by analyzing a large corpus of English text, so you can download or take some big essay you wrote, or even some maybe not Shakespearean English, but maybe some big more modern textbook, or just a regular novel or something like that, and analyzing that by counting the frequency of letters A through Z in such text, you can come up with a distribution of letters. Okay, and here's a reasonably good distribution. Okay, we are defining I guess a function, if you want to think of it as a function, but it's actually a variable variable or a name. Okay, and its type is bracket float bracket. Okay, that means it's a list of floating point numbers, and the table equals, and here's an actual table or a list technically. Okay, it's a list of floating point numbers, and it's got 26 numbers, and each number corresponds to the letter's frequency, okay, or percentage. Okay, so you can see that A the letter A appears 8.1% time in the English text. Okay. Now this may not be exact because the text corpus on which this analysis was done, in that it appears 8.1, but in a different corpus it might be 8.7 or something like that, or maybe it is 7.9. But anyway, it's close to 8 is what you would find. Okay. The B appears 1.5% of the time, and C, D, and E appears 12.7. You can see that E is the highest in all of these. And when you add all of these, it comes to 100. Okay, so this is the distribution of how often the lowercase letters appear in a normal English text. Now, you can always have abnormal English text, and actually I do have an example of a large essay written by somebody in which the letter E and the corpus or that particular essay goes to 5 or 6 pages or maybe so, something like that. See, it's a fantastic piece of it's and then in that the letter E appears exactly once. Okay, now you might wonder how can you write an essay or a story or whatever it is, but it is interesting. It appears in a very interesting book which was published in the 1980s called Gödel, Escher, Bach, GEB, by Douglas Hofstadter. He's still a professor in Indiana University. See? And this essay. Okay, so that's an abnormal text. Okay, it is written purposely by the author to just sort of defy the fact that E appears so frequently in the English language that he said, no, it does not. Here's a big essay of 5 pages, 10 pages, and I use the letter E only once. And actually, the place where he uses the E is also a joke. You see, joke in the sense that right in the last sentence and the last word, I think so. I don't remember now. After all the 5-6 pages, there at the end, just when he's about to finish the essay, he uses a word in which there's an E. Okay, I'm sure on purpose he did that because he could have avoided that last sentence and still ended the whole essay he was trying to write. Okay, but anyway, that's an aside. But the letter E appears 12 points. So let's say that this is the ground truth of the percentages of how often a particular letter appears in the English text, and this is pretty close to the actual. You can actually see, and it's quite intuitive too. Okay, so I guess E and A are the most frequent ones. Okay, and then there's a letter here. I guess that's an I. Let's see, A, B, C, D, E, F, G, H, I. No, I is that. J, K, L, M, N, O. Yeah, I and O. I guess most of the vowels will appear more often, right? A, E, I, O, and then U does not appear as frequent as some of the others. U, oh, well, maybe it does. Okay, is that U? This may be S. Okay, S, T, U, V, W, X, Y. No, this is R, S, T, U. U appears less frequently than the other vowels. Okay, anyway, that's besides the point. But let's take this as the ground truth of the frequencies. Excuse me. Okay, and we're going to use this in our cracking. Okay, so what we're going to do is we're going to take this coded text, okay, whatever is given to us, and produce a frequency table there using that. In that text, how often certain letters appear, and we're going to write some code which will do that. Okay, and then once we get the frequency table for the coded message, we'll compare that frequency table with this with let's say the ground truth frequency. Okay, we'll compare. Okay, and we'll figure out how to compare it. Okay, in a minute. And then what we'll do is we will shift the coded message by 1 position. The initial comparison will be without a shift, right? Correct, because you're comparing as it is. Then what we'll do is we'll shift the encoded message by 1 position and then compare with this table. The frequencies, again, we'll calculate the frequencies of this after we shift and with this. And so on. We'll try all 26 shifts, okay, including the 0 shift, okay, 0 to 25. We'll try all possible shifts, okay. And for each shift of this, obviously one of them is the correct answer, right? Because the shift has to be between 0 and 25. Okay, of these 26 shifts, exactly one of them is the correct shift. Okay, and we are trying to determine what that is. Okay, that's what we're trying to do. So the good news is that's only 26 shifts in this method. Okay, so we can try all 26 shifts. Okay, and but given a particular shift, okay, we need to know how to compare the ground truth frequencies with the frequencies appearing in this string. Okay, and there is a particular test for that. It's called the chi-square test, and we're going to get to that. Okay, and using that test, it's a statistical test. Okay, so if you have done some statistics, you probably have done a chi-square test, okay, which compares two distributions and tells you how close they are. Okay, got it? And we can use that technique, and actually it works quite well for Caesar Cipher. You'll see that at the end of it. Okay, so we're going to compare the frequency tables for each of the shifts with the ground truth, and then using the chi-square test, and then the closest match, we will assume that's a shift, and then we will decode it. Okay, all right. So that's the overall plan. Okay. Now to do that, we already have this table. So that's my next function. You can actually see that's my next function. It's this is not a function, but you can think of a constant list like that as a function or a name. Okay, so I've added that here. So you can see that these functions, as I'm going down, I'm adding to this file. Okay, the next one is a simple percentage calculator. Okay, given two numbers, it calculates what's the percentage, and we need that in the frequencies, calculating the frequencies. Okay. So percentage, this is a very trivial one. Given two integers, it calculates the percentage of the first integer on the second integer and returns a floating point. Okay, percentage nm equals. It takes the n and it converts it into the from integral function, which is a built-in one. Okay, in the prelude, it takes integer and converts it into float. Okay, so if you want, we can try this out. From integral. And let's say 20. Okay, this would convert the 20. I guess it keeps it at 20, but it does allow us to do integer division. So if you do type, you'll see that of from integral. Okay, yeah. So it says that it's a numeric. Okay, so it's a numeric. So basically it's a numeric, and for numerics. Let's see, yeah, for numerics, if you do division on two numerics, this one converts it to a numeric, and when you do this divide, you would the divide expects what's it called? The last type class, I think it's called fractional. Yeah, that's right. So automatically the from integral. It converts it into the fractional part, and then we would get n divided by m. Now, what happens when you just do n divided by m is the question. Okay, so let's say 5 divided by 15. Okay, this would be 0.333. Okay, which is exactly what we want, because 5 is a numeric and 15 is a numeric. Okay, 5 by itself is a numeric. Okay, because even though it's an integer, but Haskell will treat the literals as numeric. I think we saw this last time. Okay. Anyway, the question is, what if we didn't do this from integral? That's what I'm trying to see here. Okay. Let's see if we don't do this here. Okay. So we have n divided by m times 100, because that's how we calculate the percentage. Yeah. So yeah, there's a problem here, because it in the data type we said int. That's a problem. Okay, in the data type, if we had put, for example, if we had put numeric here, numeric a, like this with the type constraint. Okay, and then said a float, then this would work. Okay. Oh, didn't work. Okay, float. Okay, let's see what happened here. A float. A is a rigid typal bound by the type signature for all numeric a. Yeah, numeric does not give us the, so this has to be fractional, right? Only on fractional you can do a divide. No, doesn't work. So maybe the type here on this output, yeah, I guess we had to say a here as well. Okay, because we want the fractional in the answer, and that's how you get it. Okay, yeah, got it. You cannot put float there because you want float by itself does not have the it's not part, but you want to say it's the result you get is a fractional. Okay, if a is fractional, then a would work. Okay, and that's what maybe that's how we should have done it. Okay, uh, I think the reason we did it the other way around is because we wanted the first two a's to be integers, okay, because that's how we're going to get, okay, the inputs of these two, I guess. Okay, if you want, we can go back. What was it? Actually, we did not have any type constraint here. Okay, so we'll remove that. Let's go back to that. Okay. Anyway, that is an interesting back and forth on type safety and so on. Okay, so let's go back to the original one, int, and float. Okay, and we do want to convert this to from. We want to convert it to the numeric type from integral. Okay, that's a function in the prelude. Okay, I think we are back to the original code. Okay, if you want, we can just basically look at the type of from integral. Okay, this is a good way to check the types of built-in. Okay, yeah. So yeah, it takes. Yeah, what it does is that it takes a type A, which is of integral type, and returns type B of numeric type. So this is allows you to go from integral. Remember, integral was with the div and the mod. Okay, so type classes. The integral was div and mod. So when you provide an integer here by default, that would have only the div and the mod, and it will not have the divide. Okay, but we want to convert. We want to jump to the higher class. Okay, num what was at the superclass, right? Superclass of integral is num. Superclass of float is also num. Superclass of all those other classes. So it's all arranged in a hierarchy. If you remember, num was the most generic one of all of those. Okay. And then integral supports the mod and div. But if you provide integer as the input, it will support mod and div, but it will not support the slash. So that's why we want to convert something which is an integral into something which is a numeric. So we are going upwards in the type hierarchy. Okay. Anyway, this is something we learned, something which we didn't know. Okay. Anyway, that's all it does. So the from integral moves a value from the integral type class to the numeric type class. Okay. And from the numeric type class, we can come down to the floats, and also we can use the divide. Okay, the type theory will allow us to do the divide on those and work with that. Okay, so anyway, I guess this is a different topic. It has nothing to do with Caesar Cipher, but we learned a little bit about type theory of. I'm going to keep this from integral type here. Okay, so that. We can sort of remember this discussion. Okay, but anyway, percent is a very simplistic function. It takes two integers and gets you the percentage. Okay, 5 over 15 times 100. That's what it does. Okay, all right. Now, when we have a percentage function, and we can use a list comprehension and some of the other things like the count, which we did before, using these couple of things, and also the lowers, which we used before, we can actually get a frequency table for the coded version. Okay, remember our goal was to get a we have the ground truth frequency table here, but our goal was to get a frequency table for the coded version. Okay, and now we are ready to build that function. Okay, so here it is. Frequencies is the function freqs, which takes the coded string and produces a list of 26 floating point values, because we need to get the frequencies for each letter A, B, C, D in the coded version. Okay, only then we can compare the two tables. Okay, the ground truth with this. Okay, so obviously many letters don't appear, so those frequencies will be 0 in the coded versions. Okay, but the non-zero values is what we are going to be using. Okay, so this is nothing to do with the chi-square test, but this is just to count how many times each letter appears in the coded version. Okay, and also a percentage we'll calculate rather than the actual count. Okay, so let's look at what we're doing here. So given a string which is xs, we want to generate the frequency percentages. Okay, because these are also percentages. You can see that, right? These are percentages, okay, add up to 100. So these also need to add up to 100, okay, because only then there'll be a fair comparison between the two frequency tables, okay. Let's look at this. XS is the coded string, okay. So what we do is we count how many times lowercase letters appear in the coded string, okay, and that's because the uppercase letters don't come in the calculations, right? We said that they're not coded, so it'll be fair only to count the lowercase letters, how many times they appear, okay. So we count how many lowercase letters there are, and if your coded string had only lowercase letters, then it'll be all the letters, right? So n is the number of times the lower or the count of the lowercase letters in XS, okay. So that's the where clause n equals that, okay. And now let's look at this list comprehension, okay. It's a pretty straightforward list comprehension. What it does is that x from a through z, so it's going to go through each letter a through z lowercase, okay, and for each one of those it's going to count how many times x appears in XS, okay, because that's the frequency of how many times a appears in the coded string, okay. And using that value, the number of times it appears, and the n, it calculates a percentage between the two, okay, with this function. Very simple, okay. So if I gave, let's say, the example a 3 a's, 4 b's, 3 c's as a string, and called frequencies on that, then this is the answer I get, okay. You can see that A appears 3 times, C appears 3 times, and B appears 4 times, okay. And the total number of characters, lowercase characters, are 10. 3 plus 4 plus 3. So 10 characters, 10 lowercase characters, and A appears 3 times. So what is the percentage? 30%, right? And for B, it will be 40%. And for C, it will be 30%. And that's exactly what you see here. 30% for A, 40% for B, 30% for C. Don't worry about this 0.00002. That happens not just in Haskell, but also in C and Java and Python and so on and so forth. That's the nature of floating point numbers inside the hardware, okay. So you can never represent exactly a percentage, okay. Floating points are not exact anyway, this value of the 0.0002 extra there, the correct answer is 30, 40, 30, okay, but it's and they don't add up to 100, they add up to more than 100 here, okay. Anyway, that won't bother us in this particular problem. But if you're doing astrophysics or not astrophysics, yeah, I guess atomic physics, okay, where the distances are measured in the nanometers and nanocentimeters, nanomillimeters, and so on, then this error would be a big problem, okay. But in astronomy, this error will not be a big problem, because in astronomy we are dealing with large numbers, okay. In atomic physics we are dealing with small numbers, okay. Anyway, this is the frequencies, okay. So we have a function, and that's the next function here, frequencies. Where is it? Here, okay. So frequencies takes a coded string and generates a table which looks exactly like this table, which is the ground truth table, which is hard coded in our program, assuming that we did some analysis on some plain text. And if you want to do that analysis on your own, you can write your own Haskell program to read the Shakespearean some novel, and then count how many times a letter A, B, C, and then you can generate this table for yourself, okay. And maybe that's a little bit more accurate than this, and maybe whatever it is, okay. But this is the table, and then the frequencies allows us to calculate a similar table for the coded text, okay. So we are done, all of these functions we are done, okay. So I think only 3 more left, okay, and we'll solve the whole problem, okay. So any questions here? So that's the frequencies. Now we are ready to do the chi-square calculation, okay. Let's see, now we don't really need to understand the details on why this works and so on. What is this chi-square statistics and what, but we want to know the formula at least, okay. So this is the formula here, okay. Chi-square statistics is a standard method for comparing lists of observed frequencies, let's call that OS, with a list of expected frequencies, which is called ES, okay. And in our case, the expected frequencies is this one here, okay, the table here. And the observed frequencies will be the output of the frequencies, FREQS, on the coded string, okay. So, and both of them have the same number of items, which is 26, okay, 26 floating point numbers, okay. So this statistics is a pretty simple one. All it does is that it's a sum of I going from 0 to n minus 1. In this case, n will be 26, so 0 to 25 of OS, which is the observed frequency, minus the expected frequency, square of that, okay, the square, so that negative numbers don't show up, so square will get rid of the negative, so it doesn't matter if it's this side or that side, the frequency, how far away from the expected value it is, that's all, okay, and then divided by the expected value and sum up all of these for each I, okay. This is called the chi-square statistic, okay. The details of this is not important, but the one thing we need to know is that the smaller the value of the chi-square statistic, the better the match between the observations and the expected values, okay. So smaller, that's what we need to know, okay. So let's see how to code this statistics first of all, okay. So here is the observed, I guess the first one is the observed, okay, and the second is the expected, okay. So the first list of floats is an observed OS, and the second list of floats is the expected, okay, which is our expected table, which is pre-generated. And we want to compute this formula, okay. This formula will actually return a single number, a single value, okay, right, because it's going to be a sum of the squares of the differences of the corresponding values divided by the expected value, and it's going to be the sum of all of that, okay. So it'll end up in a single number, okay, a single value. And we're going to do this many times for different shift factors, I guess, and then we will find the one which is the smallest, because the smallest is the one which is a better match, okay. So this chi-square actual body of this is coded with a list comprehension, very straightforward. All you do is take the observed and the expected arrays or lists, okay, and zip them, okay, because both of them have exactly 26 values. When you zip them, the corresponding pairs, okay, the OS of I and ES of I will be paired together in a pair, and those will be these two values, O and E, okay, and O and E will be for each index in the zip, you will get the O and E, and here we are doing O minus E squared divided by E, okay, and we'll get a list of all these values, and then when you do sum, that does the sum, this sum here, okay. So chi-square, this is a very simple list comprehension which calculates the chi-square value given two lists or two frequency lists, okay, OS and ES, okay. All right, so now we have a chi-square calculation already done in this, and that's this function here. When you go back to this here, that's this function. Now we are almost there, okay. Now if you remember, our strategy was to take the coded string, rotated by shifted by 0 positions, which is the same thing, we know shift, shifted by 1 position, shifted by 2 position, and so on. So try all possible shifts, okay. So we need a method or a function which will try a shift, okay, or which will actually shift by a given position n, okay, shift factor. So that's what this rotate does, okay. Rotate, what it does is that it gives, given a shift factor int, and given a list of A could be anything. In our case, it'll be the coded string, okay. The coded string will be given, okay, and the integer shift factor will be given. And what it does is that it rotates this string to that. In some sense, this is very much like the encoding and so on, okay. But yeah, I guess it's the same, maybe, okay. No, and this is different. Now this is different because this is going to rotate the chi-square values, okay. Okay, we'll see how it is used, but it just takes a list and rotates it by that position, okay. And you can actually imagine what's going to happen. We're going to have the frequencies calculated for 1, and then we're going to shift the whole thing by 1, okay. We'll use a shift factor of 1 and then shift it, and then shift factor of 2 and shift it, and so on, okay. But anyway, this rotate function is independent of that. All it takes is that it takes a list of items and rotates that list around by certain positions, okay. So, and it's a very easy implementation. N and XS, drop N XS plus take N XS will rotate it. Okay, so here's an example. If you want to rotate the list 1, 2, 3, 4, 5 by 3 positions, uh, you take 3 and drop 3. So when you take 3, you get 1, 2, 3. And when you drop 3, you get 4, 5. And then you flip them around and you attach the take 3 after the drop 3. Then what will happen is that the 1, 2, 3 will come after the 4, 5. You get 4, 5, 1, 2, 3. And this list is essentially the original list 1, 2, 3, 4, 5 by rotating it by 3 positions. Okay, rotating means you take the 5 and bring it here. One position will be 5, 1, 2, 3, 4, and the two positions will be 4, 5, 1, 2, 3, or 5, 4, 1, 2, 3, 4. Okay, if you want to shift it to, then it'll be, yeah, I guess 4, 5, 1, 2, 3, 1, 2, 3, and that's really what has happened here. And as rotating 0 would be keeping it as it is. Okay, so that's just a rotating a list by a certain number of positions. Now, suppose now we are almost ready to actually solve the problem. In particular, how to get the new table, okay, and also how to get the chi-square calculations, okay. This is not part of the code, but this is going to be, these two statements are going to be useful in the code, the final function we write, okay. But now let's look at the final step here. Suppose that we're given an encoded string, okay, but not the shift factor, okay. We can determine the shift factor by producing the frequency table of the encoded string. You do that. Then calculate the chi-square statistics for each possible shift. Okay, got it? After you get the frequency table, and calculate the chi-square the same calculation for that. Okay, and factor would be 0, 1, 2, 3, 4 up to 25. Okay, for each possible shift, and then using the position of the minimum chi-square value as the sigma. Okay, so the minimum chi-square value is the best match. We said that, right? And that's what we'll use as the shift factor, and we can crack the code. Okay, all right. So suppose you had table prime. Okay, table prime is the observed frequencies. That's what this is on the Haskell is fun coded string. Remember? So what table prime would be, it'll be something like this, okay? Table prime will be, no, it won't be this, it'll be the frequencies, okay? So maybe we can actually say table prime just to see what its value is before we look at the chi-square. Oh, interactive values are not allowed, so maybe we should, I'll remove this guy here. Yeah, do that. So I'm calling frequencies and I'm also doing something else. Yeah, I guess, let me put a comment here for a moment, okay? Yeah, frequencies of that. So that gives us, oops, oh, frequencies was not defined, so maybe we need to run the frequencies here, this one here. There you go. Okay, so these are the frequencies, percentages for A, B, C, D for this. And you can see that only the K, V, H, O, L, V, those things got non-zero values. Everything else has got 0 values, okay? And the interesting thing is most of them got 8.33, which is one occurrence. I think 16.66 is 2 occurrences, okay? Here there are either 1 occurrence or 2 occurrences. There are no 3 occurrences of the same thing, and that's why you got these percentages, okay? So this is the frequency distribution for A through Z of the letters A through Z in this one, okay? Now, let's say that this is table prime, okay? That's what we had, right? Table prime equals this. And then we do the chi-square. Okay, what we're doing is for each of the rotations, we're going to calculate the chi-square, okay? And then we're going to produce a list of all the chi-square comparisons for each of those 26 shifts, okay? So n ranges from 0 to 25. And what we do, we rotate the table prime, which is this frequency thing, by 0 positions, 1 position, 2 positions, 3 positions, and so on. And we compare the table we get with the ground truth table using the chi-square calculation, and we get actually a value, okay? So let me run this and you'll see, oh, okay, what happened here? Oh, this, oh yeah, table prime. This is table, oh, okay, I guess I did not run this table also. Yeah, this needs to be run. Yeah, that happens when you don't run the cells. I think now we are good. Let me reach this point. There we go. There we go. We got it, okay? So this table is the ground truth, and this one here is the frequency counts, which is table prime of the encoded, but rotated by a certain position. Okay, got it? So we don't know which is the shift. Okay, but so we are going to calculate all the frequencies. So this value is going to be different tables for the different shifts of the frequency counts of that. Okay, and we're going to do the chi-square of this frequency counts with the ground truth, and we're going to get a chi-square value. So without any shift, we got 1408. Okay, with a shift of 1, we got a chi-square value of 640. Okay, with the shift of 2, we got this, and so on. With the shift of 25, we got 626. Okay, all of them are comparing with the table, which is the ground truth. Okay, and if you look at this, the smallest value of all of this is here. Okay, 202. Okay, and our guess is that this is 0, 1, 2, 3. Okay, those are the shifts. Okay, so in index 3 is the shift 3, which is what our guess is that that's the shift factor. Okay, and actually it was the correct shift factor, if you remember. Okay, so what we'll do is we'll find the minimum values, the smallest value of this list of chi-square comparisons, and use the index for that, and use that as our guess for the shift, and we will decode it. Okay, all right, so I think we are ready to write the final function, which is the crack. Okay, and let's look at this. This is the final function. Crack takes the encoded string and produces the decoded string, okay, by guessing the factor and applying the factor. Okay, here it is. Crack of XS encoded string, it guesses a factor, okay, which is in the where clause, okay, and takes the negative of that. Okay, why? Because encode negative is the decode, right? Encode of negative of factor of XS is the final answer. Okay, and what is factor? Factor is defined as follows. Okay, there are 3 variables here. Let's look at table prime. That's a table prime is the frequency counts for A through Z in the, it's not just the count, but it's the percentages of the counts. Okay, the frequencies, because the 2 tables must have similar percentages. Okay, because the table is a list of percentages which add up to 100. Frequencies also should have that, and that's why we calculated the percent. Remember, so a table prime is the observed frequencies, and table is the ground truth frequencies. So table prime is that variable, and chi tab is the chi-square table, okay, which is a list of chi-square values of the rotate and table prime with table, where n ranges from 0 to 25. So you're going to try all possible shifts and calculate the chi-square values, which are these kind of values. And here in the factor, we're going to take the chi tab, which is this table here, and we're going to find the minimum of chi tab. Minimum is a built-in function which given a list finds the minimum value. Okay, and positions is, it'll try to find where all this minimum value appears. Now the minimum value might appear more than once. In this case, it appears exactly once in this position, but in case it appears more than once, positions will tell you where all it appears. And the first one, I guess we want to pick one of them. If not, we may try the second one, but we just go with the first one, and that's why we have the head here. Head gets you the first of those positions. Okay, so this whole expression finds you the index of the smallest value of the chi-square values available in this chi table. Okay, which is the factor. Okay, and that factor is used here. Okay, and there you go. Okay, so this is a crack. Okay, now we are proof is in the what is that in the proof is in the pudding, or whatever, there's a phrase like that. So let's try this out. Okay, so I'm going to run this. Okay, variable not in scope. Which one is that? The encode. So I guess I had to go all the way back to the top and run that cell here. Yeah, I guess I can start from this one because this is where we began. Chi-square rotate. This is the simple small calculations, and this is a crack. Yeah, there you go. Now we have crack, and now I want to crack this. Okay, so when I run this, I get Haskell is fun. You see this coded string has come out here. Fantastic, seems to work. Okay, so given this coded function, we guessed correctly the -1 using chi-square calculations, and we also decoded it and got Haskell is fun. Here's another example. Here's a string list. Okay, now I didn't want to do 2 steps, so what I did was I took a string, list comprehensions are useful, and encoded it with a shift factor of 6. I should get a coded string, and then I cracked it. Okay, so this crack does not take the code. So and then when I do that, I should get list comprehension of 6. So this is going, and then I got it back, which means that the crack is working. Okay, got it. Now when I take another one, the Lakers beat the Warriors by 2 points. Okay, and encode that with 5, and then crack it, I get back this. Okay, that's great. So it looks like it's working. Now I can also encode it with some other 12, and let's see whether it works. Okay. Yep, it does work. Okay, with 12 too. Okay, if the code where the crack if the shift factor was 12, it still works on this string. Okay, and so on. Okay, so it looks like we have a working program which cracks codes. Okay, given any coded string, it makes a good intelligent guess on the shift factor and decodes. Okay, now life is not so good. Here are a couple of examples where it doesn't work. Okay. So the observation here is that for some small strings and for some unusual distributions, for example, that distribution, the Gödel-Escher-Bach textbook, the person who wrote the whole essay for 5 pages without using the letter E. Now, if that was coded and and that coded text was intercepted, this method will not work on that, because this method assumes that the E appears the most frequent, and that person deliberately wrote an essay without E. Okay, so for unusual distributions and for also small strings. Okay, for big strings this would work easily, and for almost all the case. Okay, so Haskell is a small string. When I encode it with 3 and then crack it, I don't get Haskell back. You see that? Even with some other, let's say 12, I probably get something back. I got back the same PIA. Okay, so I'm not getting the correct answer here. Okay. Here's an unusual string. This is the string which boxing wizards jump quickly. I think the W and the Z and the P and the Q are used more frequently, I guess, or whatever it is. Okay. So this also doesn't work. Okay, so you don't crack it here. Okay, so what does it mean? It means that our method, the chi-square distribution, works most of the time, but not always. Okay, but in cracking the code, it's always practical to get a working solution which doesn't work always, but works most of the time, right? Because when you fight a war and you are intercepting messages, if you got the 90% of the messages you are able to intercept, that's a good thing. You have advantage in the war, right? So that's what this method does. Okay. Anyway, it's a long story short. We have a working program which is seen here completely. See in this whole screen here, starting with the import with all these 13 functions, which ends there. We have a working program. What you can do is you can take this, and I did put this into a file. So let me get to a file here. So it's in the Cipher. So and I can get to GHCI Cipher.hs, and I log in, not log in, sign into the interpreter, and it loaded without any compile error. And now I can start cracking. Okay, crack. Now the way I had to do is I'm supposed to give a coded version of the string, right, for the crack. Okay, but I had to do it in 2 steps. But I just I'll encode with, let's say, the shift factor of 18. Professor Sundararaman is a tough but fair professor. How about that? Okay, I hope you guys agree with that. So I'm taking a string, encoding it with 18. Okay, and then I'm trying to crack it, and yep, I got it back. You see? Now, if you do want to see just the encoding part of it, okay, I copy that and paste here. And this is the code this is the code we get. Okay, so this is the coded version you intercept, and if you want to crack this, you get that. Okay, so that's really the 2 steps, but I'm combining the 2 steps in by encoding and then cracking it. Okay. Okay, so this is a very interesting program, which I would say that works 99% of the time on Caesar Cipher, assuming, but there are much more sophisticated ciphers which are available, by the way. Okay, anyway, this is an interesting exercise, but I think the moral of the story or the moral of this chapter, which is list comprehension chapter, is that list comprehensions are very powerful mechanisms in Haskell, but in general in other languages as well, including Python, by the way. So you should start using list comprehension in Python also, okay? I'm not sure about Java, but certainly Python has list comprehensions. So you should try to use those in your, and when you start using those, you're actually using functional concepts in Python, okay? And so I think that there are two morals of the story with this particular Caesar cipher example. One is that list comprehensions are very powerful mechanisms in functional programming, and you should learn them. You should become a guru of list comprehensions. And second lesson is that functional programming works by building smaller functions and developing and combining them in ways. You can actually see that the crack function needs the built-in head. It needs the positions functions which we wrote. It needs a minimum function which is built in. It needs a chi-square function which we wrote. It needs a rotate function which we wrote. It needs a frequencies function which we wrote, and so on. Okay, it needs a table which we wrote, or the ground truth. And then the frequencies itself needs a percent function which we wrote, a count function which we wrote, and so on. So it's building smaller functions to bigger functions, and so on. So you can actually, it'll be very interesting to draw the dependency graph, which function depends on which other function for this Caesar cipher. It's a very interesting exercise which I would certainly ask you to do. Actually, this morning I drew a dependency graph for all the functions which are here. There are 13 functions which we developed, and there are another 10 or 15 functions built in which we have used, like ORD and so CHR and so on. So if you look at all the functions, there's about 25-30 of them here in this solution. And if you drew the dependency chart of this, at the bottom level you'll see the prelude functions, and then at the top level you'll see the crack function, crack. Okay, and it's a beautiful dependency graph which shows you, that's the moral 2 of this exercise, tells you the style of function programming and how function definitions and function applications are used as a model of computation. Okay, all right, time to stop this video, and that's the end of chapter 5. All right, let's see. Let me get to the